Hello friends. Today we will discuss and derive the simultaneity in relativity. Now, first of all, let us try to understand what is the meaning of simultaneity. Now, what is the meaning of simultaneous? Okay, simultaneity means occurring at the same time. Okay, if suppose there are two events, if they occur at the same time, that means the event are simultaneous. Okay, so this is very important topic in the context of relativity. Okay, now suppose we have two inertial frame of references. This is frame 1, that is known as S frame, x-axis, y-axis, z-axis, region O. Okay, now suppose there are two inertial frame of references, frame S and frame S dash. Now S is a stationary frame. Okay, S is a stationary frame. Now meaning of inertial frame means I have discussed in previous relativity lectures, that is which obeys the laws, Newton's laws of motion, that is which obeys the inertial law of inertia. Okay, so S is the stationary frame of reference, S dash is the moving frame of reference. But initially both the frames are at the same position. Okay, now this is S dash frame, X axis, X dash axis, Z axis, Z dash axis, okay, or Z prime axis. Okay, now initially at time t equals to t dash, at time t is equals to t dash equals to 0, both the frames are at the same positions, that is O and O dash. Okay, origin is same, but after that S dash frame starts moving. With a uniform velocity v, suppose along x-axis. Okay, S dash frame starts moving with a uniform velocity v along x-axis, and here is the stationary frame. Okay, and now axis is x, y, z, o. This is stationary frame. Initially both the frames are at the same position. Now, for example, there is a 100-meter race and race between two athletes. Okay, athlete 1 and athlete 2. Initially they both are at the same position, and one athlete starts to moving after a certain time. Okay, and suppose this remains at the same position. Now this is the moving athlete, moving frame, and this is the stationary frame. Fine. Now suppose two events in frame S occur simultaneously at position P1 and P2. Two events in frame S occur at the same time. That events, maybe suppose this observer has two pens, and suppose he has thrown two pens. Okay, so these events occur at the same time in the frame S. The coordinates of this position will be x1, y1, z1, and t1, and for this it will be x2, y2, z2, t2. Okay, now events will be simultaneous, occur at the same time according to observer in frame S. According to this observer in frame S, these events occur at the same time, that is t1 equals to t2. This is equation number 1, that is t1 equals to t2. Okay, now question here arises that will these events be simultaneous from frame S dash? If there is observer O dash in frame S dash, then will these events be simultaneous from this frame also? Okay, will t1 dash equals to t2 dash or not? Okay, this we have to prove, okay, under relativity concept. Now let us start this discussion. Now according to the Lorentz transformation equations of time, that is t1 dash equals to t1 minus x1 v upon c square divided by the root of 1 minus v square by c square. This is our equation number 2. This result I have derived earlier. So this is from the Lorentz transformation equations, okay, for time. This is for Lorentz transformation equation for time. Okay, t1 dash equals to t1 minus x1 v by c square root of 1 minus v square by c square. Now t1 dash is the time for the event first, that is p1. T1 is the time from the frame S, okay, for the same event. X1 is the position of the event, okay, from frame S. V is the velocity of the S dash frame. C is the speed of light, okay. So similarly t2 dash for the second event, t2 minus x2v divided by c square root of 1 minus v square by c square, equation number 3. Okay, now subtract equation 2 from 3. Subtract equation number 2 from equation number 3, that is t2 dash minus t1 dash equals to t2 minus x2 v by c square root of 1 minus c square by c square minus t1 minus x1 v by c square root of 1 minus v square by c square. Fine. So t2 dash minus t1 dash equals to t2 minus x2v by c square divided by root of 1 minus v square by c square minus t1 x1 minus v by c square divided by root of 1 minus v square by c square. Just rearrange the side, it will become t2 minus t1 divided by root of 1 minus v square by c square minus v by c square x2 minus x1 minus v by c square. V by c square is common here. It is common here. Minus v by c square x2 minus x1 root of 1 minus v square by c square. Okay. Okay, just rearrange these sides. Now from equation number 1, what was equation number 1? T1 equals to T2. Okay, now use equation 1. If T1 equals to T2, then this term will become 0. This term will become 0. So we will get T2 dash minus T1 dash equals to minus v by c square x2 minus x1 divided by root of 1 minus v square by c square, equation number 4. Okay, now as these two events even from the frame S occurring at different positions. Now those different positions are x1 and x2. Okay, these two events occurring at position x1 and position x2. So these positions are different. So x1 is not equals to x2. If x1 is not equals to x2, then this right side will not be 0 because c is not 0. V is the velocity of the frame S dash. Then T2 dash minus T1 dash will not be 0. Okay, if this will not be 0, it means T1 dash will not be equals to T2 dash. Now this is very interesting concept. We have we have studied that t1 is equal to t2. That is, the events which are simultaneous from frame S is not simultaneous from frame S dash. Okay, will not be simultaneous from the frame S dash. That is, the events will not appear to occur at the same time from frame S dash. Okay, so this is the concept of simultaneity in relativity. Okay, that is, event will be simultaneous from one frame, but it will not be simultaneous from the another frame if the object is moving with a speed comparative to the speed of light. Okay, I hope you have understood. Thank you. Thanks a lot.